Maybe you notice that this function, its derivative is sitting right here. Yeah, it's a very obvious example of integration by substitution. Anytime you're integrating, you're trying to undo a derivative. You're trying to anti-derive. You're trying to notice something that was in the original function and trying to work back. So you probably could work back this one, maybe work back this one, just logicking it out. Yeah, because we know that the original function must have had this in it for this to have been part of the derivative. And what was the original power, maybe?
3 over 2, yeah.
The original power was 3 over 2, and it worked down to a half. That would make sense. Any multiplication in front or anything like that?
Yeah, there was a coefficient.
Yeah, so what would the coefficient, how would we, 2 over 3?
Yeah.
Okay. Well, let's see. That we can kind of undo it. I'm going to show you this technique of integration by substitution, which will help us solve more difficult ones like this and more difficult ones like this. Which maybe I'll just do. So I'll do an example that we probably could anti-differentiate or just logic it out. Like you guys, I think you pretty much had it. All right, so first of all, we nominate something to be, we're going to substitute and integrate something easier. So I'm going to nominate one of the functions to be u. I'm going to substitute u in for that because u is easier to integrate than this whole thing. And what I'm going to do is, because it's anti-chain rule and there's derivatives involved here, I'm going to actually derive this function. Derive u first. And I get 3x squared plus 2. And you'll see why I do this in a second. Oh, you're ready? Yeah.
No, I have a question about how is root x cubed plus 2x the derivative of 3x squared plus 2?
No, ignore the root. Ignore the root.
Oh, the thing inside.
Because remember,
under the root.
remember for chain rule, the power here would be a half, and then you'd multiply down, and then you'd afterwards.
There was no 1/2, so I was just.
Oh yeah, okay, yeah. Yeah, there's no 1/2, so we have to be able to deal with that as well.
Yeah, why? Why is there no 1/2?
Because there must have been some 2 or something in the original. Yeah. Okay. I'm going to do a little rearrangement. So the idea here is every single part of this I want to substitute with some u function because u is going to be easier to integrate. So I have every single part of this. Now, so far this could be substituted. This I could replace with du over dx, but if I do a quick cross multiply of dx, I get this. So dx, just multiply both sides by dx, and I have this, which is the same as that. Yeah. Yeah, you were doing this when we did last year, dy dx. Yeah, we're doing dy dx, and we're splitting up trying to get the x's one side, y's the other side. Yeah, it's just infinitesimal changes in x. I know it's a group of them, but maybe it doesn't make sense as when we're in algebra, but it does make sense. Okay, now I have everything I need to do to substitute. I still haven't integrated anything, but watch the substitution process now. This can be replaced with u, so I have now square root of u, which probably better off with writing u to the power of a half, times, well, all of this is du. So every x in the original has been replaced with some version of u. It's a bit like when we go to solve a trigonometric. We have sine x squared plus 3 sine x plus 2. And you want to solve this. So you say, all right, I'm going to exchange the variables. I'm going to say a is sine x squared and just make it easier for me. Or sine x, sorry. And we go a squared plus 3a plus 2. And we solve this. But we really know that a is sine x at the end. So we come back to it. And that's what we're going to do here. We're going to come back to what u is at the end. So integrating this is a piece of cake. We just add 1 to the power, 3 over 2, and divide by the new power, 2/3, not 3 over 2. I forget who did that. Josh, maybe. Plus c. You did. You had 3 over 2 earlier on in the race thing. Okay, so I've integrated. It's easy to integrate just a single function like this, or single.
The integral of du just u.
The integral of du. Yeah. Okay. No, remember, this is terminology. This is terminology. These bits are terminology. So when I integrate, I'm going backwards for derivatives. So there will be no d.
Yeah, that's what I just said.
Oh, okay, yeah. There is no u either.
No,
But
you just said it.
okay.
You said it's the integral of du.
Am I finished? No. I must sub back in my u. Same as this. When I get to the end of this thing, I don't get. If a equals 1, it's not a, it's sine x equals 1. Same here, I've got to put back in for u. So 2 times x squared plus 2x, that was my u at the start, to the power of 3 over 2 over 3 plus c.
That's it?
Is it? Yes.
Wait, what happened to the
so easy.
What happens to the dx when you integrate all those other questions? It was the same thing. We think about it as term.
in the first place?
Yeah.
Oh, you wrote it.
Yeah.
You wrote it.
Did I write it wrong?
X3. You wrote X3.
Oh, did I write? Sorry. Excuse. Okay. So now we know where the 2 would come from. You know, you were saying, oh, there must be some sort of 2 to cancel out, so it would be 2 over 3 would be the thing that would have cancelled out.
So wait, what's the integration of du? No,
All the time you've been working with integration with dx at the end of it, and you haven't thought anything about it because it was the terminology we were dealing with. Now it's just if the function is in u, we want to integrate it with, this means with respect to u. You're looking at u on the x-axis, not the x-axis anymore. You've called the x-axis u-axis. The infinitesimal changes in the u-axis, you've called the x-axis u.
So we just ignore the du when integrating?
Pretty much, yeah. It'll go away, yes, because you're undoing that process. Okay. Let's do this second one. So what the main problem is, maybe what do I pick as u at the start? And that's the problem here. We're looking at this second function. What do I actually call u? What's the thing I'm going to make u? Any suggestions?
Good question, sir.
Wait, what was your question?
What do we? So I just picked u at the start. I picked it.
Let's do e to the 1 negative.
No, that won't work.
1 to the negative x.
Oh,
squared.
should u be 1 minus x squared?
Yes. Yes. Not e.
Well, I said it.
No, Alex, calm down. You said e to the power of. No, not. I'm going to pick this function as u.
Oh, because the derivative of that is x.
Because the derivative of this will have an x in it.
Yeah.
And I want to get rid of this x. I could rewrite this function e1 minus x squared times x dx if I want, or some version of this. So what I want to do is have x dx, and e to the u is easy to integrate. So I'm calling u 1 minus x squared. The same process as here. What's the next step? I just always will derive this to get a du into the equation. And I get, what's the derivative of this? Negative 2x. Now this is where it starts to get a little bit more difficult. Because you notice it's not the exact same. When I multiply over by dx, I get minus 2x dx. Now I didn't want minus 2x dx, I wanted x dx.
So you divide by negative 2.
You divide by negative 2. So if you divide both sides here by negative 2, or you could say multiply by negative 1/2. People prefer that sometimes. I get x dx on this side. Or divide both sides. You can write du over 2 if you want.
Wait, why in the second step? Why did you just take away the x?
What?
Oh wait, no, you put on there.
Just rewrite it.
Yeah. Okay. So my steps here: multiply both sides by dx, cancels this dx, and then multiply both sides by negative 1/2. Why did I do it? Because I want this to be the same as this. See, this is an x dx here. Now it's the same. Now it can be substituted for. And now my entire function, same as this time, can be written in just u. So, e to the u times negative a half du. Now, our knowledge of integration, if I'm multiplying anywhere by a constant, can that constant just sit out the front? Yeah, you see, you can just sit the constant out the front. Well, okay, well, let's... You're ending up just multiplying by it, so you don't need to take it into account. You can multiply by it afterwards or before.
That's smart.
Yeah, so if you integrate anything, what's the integral of 2x dx? It's 2x squared over 2 plus c. Okay, what's the integral of 2 times x dx? Put the 2 outside. I get 2 times x squared over 2 plus c. So you get the same thing, don't you? The 2 is just multiplied in either before or after. It's often easier to do it after, so you don't have to worry about it when you're integrating. So I'll write it like, you don't have to do that. Yeah, you factor out a constant. You can put a constant out in front, factor out the constant. Right, we know the derivative of e to the u is, or integral of e to the u is e to the u, isn't it?
Yeah.
So it was easy anyway. We didn't have to pull this out in front. So that's just e to the u plus c. And what was u? 1 minus x squared. So my answer is minus a half e to the 1 minus x squared plus c. Just replace the u with what I said it was at the start. So the integration part of it is the easiest part, because that's the whole point. You're making it much easier to integrate because you recognize that it's kind of a reverse chain rule.